Okay, so this lesson is called Modeling with Quadratic Equations. So this lesson is going to be all on writing the rule of a quadratic function based on given information. So for example, if I told you that there is a linear function that has a y-intercept of 4 and a slope of 1/2, you could immediately write the rule f of x equals 1/2 x plus 4, right? It's a very similar idea. So if I have, for example, a point on a parabola and I have the vertex of the parabola, then I can write the function in vertex form, which is y equals a times x minus h squared plus k. Now, when I write the rule, I have to replace a, h, and k with numerical values, with numbers, and I have to leave y and x. So essentially what I'm going to do is replace the h and k with the values that I have, and then I'm going to use the point. This is just a random point on the parabola, x comma y. I'm going to replace x and y with this point with those values, and then use that to find a and write the rule. If I have a point and the two x-intercepts, p and q, I would write the quadratic in intercept form, which is y equals a times x minus p times x minus q. And I would need to know the a, p, and q values. So again, just replace p and q with whatever values I have, and then this point, which is just a random point, x comma y, I would replace x and y in this equation with those values and then solve for a. The last method, or the last type of quadratic equation that I could write, quadratic rule that I could write, would be the case where I'm given just three random points of, or three random points that are on a parabola. In this case, I have to write and solve a system of three equations in three variables using standard form. So this is kind of going back to something we did before. And standard form is y equals ax squared plus bx plus c, and the three variables that I have to solve for are a, b, and c. Okay, so let's just go straight to an example. Here the graph shows the parabolic meaning parabola, path of a performer who is shot out of a cannon, where y is the height in feet and x is the horizontal distance traveled in feet. The performer lands in a net 90 feet from the cannon. What is the height of the net? So I see this scenario outlined in the graph, and the part that they want us to answer is what is the height of the net? And that's represented by this point here, which I know for sure the x value is 90, but I can't say definitively what the y value is. I could estimate that it's something like maybe 21 or 22, depending on how you look at it, but I don't know for sure what the y value is, just based on the graph. I know I have the vertex of the parabola, and I have the y-intercept of the parabola, but that's pretty much it. So what would be useful right now is if I had the function, the rule, that represents this parabola, because if I did, then I could just plug 90 in for x and solve for y. So that's what I'm going to do. I want to write the rule that represents this parabola. So what do I have? We already identified that I have the vertex, 50, 35, and I have this point. So I'm going to use vertex form. So I begin by just writing that out. I have y equals a times x minus h squared plus k. My vertex, right, is 50, 35, so that's my h and my k value. And then my y-intercept is just x, y. So I'm going to take all that information and I'm going to plug it into this equation, and then you'll see what we have. So it'll be 15 equals, I still don't know what A is, 0 minus 50 squared plus 35. Now, why is it important to plug everything in? Because now I have an equation in terms of just one variable, in terms of just one unknown that I can solve for. So I'm going to start by subtracting by 35 on both sides, which gives me negative 20. I'm also going to do 0 minus 50, which is this negative 50, and negative 50 squared is 2500A. Then divide on both sides by 2500, and we get, just going to use my calculator for this, you guys can as well, 20 divided by 2500, which is 0.8, but if I want it as a fraction, 1 over 125. That'll be negative 1 over 125. Okay, so now that I have my A, H, and K value, I can write the rule that represents this function. What is the rule that represents this function? It is, where should I write it? I'll put it here at the bottom. It is f of x equals negative 1 over 125 times x minus 50 squared plus 35. Now, just to make a point, let's graph this on Desmos. Y equals negative 1 divided by 125 times x, not times, x minus, I think it was 35 plus 50. Nope, other way around, minus 50 plus 35. Okay, now the 2 points we had were 0, 15. Okay, so far so good. That's a point on the problem. And 50, 35. Also a point on the problem. Perfect. Now I could at this point also just look at the graph and say, okay, when x is 90, what's the y value? It's 22.2. Or I could also just, if I don't have access to a calculator, could also just plug 90 into the function rule that I have. So f of 90 would be negative 1 over 125 times 90 minus 50 squared plus 35. I'm going to use my calculator again. So that's negative 1 divided by 125 times 90 minus 50 squared plus 35. And I also got 22.2. So, what is the height of the net? The height of the net is 22.2 feet. Now, this is a word problem, so you should write your answer in terms of a sentence, not just leave it as 22.2 feet. All right, moving on. Example 2. A meteorologist creates a problem to predict the temperature tomorrow, where x is the number of hours after midnight and y is the temperature in degrees Celsius. Write a function f that models the temperature over time. What is the coldest temperature? Okay, we'll deal with A first and then B. So, if I want to write a function that models the temperature over time, that models this scenario that I see over here on the right, I have to first identify what information I have. So, I have the x-intercepts and I have a point. So I'm going to use intercept form. Y equals A times x minus p times x minus q, where this is my p value, this is my q value, and this is my x and y value. Now, it doesn't matter if I made this my q value and this my p value. That part doesn't matter. Okay, so I'm going to take that information and I'm going to plug it in. So 9.6 equals A times 0 minus 4 times 0 minus 24. This is going to give me 9.6 equals 4 times 4 is 16, and 8, 96a. Divide on both sides by 96, and you get 1/10 or 0.1. So now I have all the information I need to write the rule. Now it specifically says write a function f, so I'm going to write it as f of x equals 1/10 times x minus 4 times x minus 24. This is the function that models this. Again, I can go to my graph and type it in. Now, it doesn't matter if I do f of x or y. It's the same thing. So we have y divided by 10 times x minus 4 times x minus 24. Okay. The y-intercept should be 0, 9.6, which it is. X-intercept is 4, 0, and 24, 0. Now, if this is asking me what is the coldest temperature, anytime you have extremes, coldest, smallest, largest, anything like that, essentially what you're being asked to find is the vertex. More specifically, the y value of the vertex. Now, if I look at the graph, I could kind of assume that the coldest it gets is -10 just from looking at this. But let's pretend I can't assume, because maybe I'm wrong. If you have access to a graphing calculator, you could look at the vertex here and confirm that it is -10. What if I didn't have a graphing calculator? Well, remember then, I would have to find the vertex. So if this is intercept form, to find the vertex, I need to first find the axis of symmetry, which I could find by taking the average of my x-intercepts, in which case I do get 14. And then to find the y value of the vertex, just plug that value, 14, into my function, into my equation, and again, I get -10. So what is the coldest temperature? The coldest temperature is -10 degrees Celsius. All right, very good. B, what is the average rate of change in temperature over the interval in which the temperature is increasing? Compare the average rates of change. Okay, so average rate of change is essentially slope, which we've already discussed in previous lessons, is just y2 minus y1 over x2 minus x1, which is the change in y over the change in x. And another way that you could think about it, which is oftentimes how you're going to see it represented in higher level classes, is f of x2 minus f of x1 over x2 minus x1. And remember, f of x is just another way of saying y. So this and this are basically saying the same thing. Not basically, they are saying the same thing. Okay, so what is the average rate of change in temperature over the interval in which the temperature is decreasing? Well, remember that if we are looking at this graph from left to right, the temperature is decreasing from here up until the vertex. So at the vertex, 14, -10, the temperature is decreasing. And then from here, the vertex, to the end, it is increasing. So if I want to compare the average rates of change, I am going to be looking at, or I will be using these points to calculate the slope. Now, obviously, this isn't a linear function, so you can't really talk about slope, but you can talk about the average rate of change, right? It's not changing at a constant rate, but you could talk about what's the average rate at which this is changing, okay? So we're going to break it up into two pieces. We're going to talk about where the function is decreasing and where the function is increasing. So for decreasing, we're using this point and the vertex. So the y2 could be 9.6 minus a negative 10 because that's y1. And then 0 minus 14. This could represent the slope, or let's not call it slope so we don't get confused. Let's call it the average rate of change. Okay, so that's going to be 9.6 plus 10, so 19.6 divided by negative 14. Gives us negative 1.4. And then for increasing, we're going to do the same thing, but use the vertex and the x-intercept. So here the average rate of change. Again, the order doesn't matter too much, so do with it what you like. I am going to do 0 minus a negative 10 over 24 minus 14. So that will be 10 over 10, which is just 1. Okay, so here we found the average rate of change for where the function is decreasing, where it's increasing, and we want to compare the average rates of change. So what we could say, based on what we're seeing, is that the temperature decreases at a faster rate in comparison to how quickly the temperature increases. That is what we would say for this question, or not this question, this directive. Okay. All right, so I'm going to skip this for now. We'll come back to it later. Let's go to example 3. NASA can create a weightless environment by flying a plane in parabolic paths. The table shows the heights, h of t in feet, of a plane t seconds after starting the flight path. After about 20.8 seconds, passengers begin to experience a weightless environment. Write and evaluate a function to approximate the height at which this occurs. Okay, so I want to write and evaluate a function, and all I'm given is this table. So I definitely don't have any x-intercepts, because if I did, I'd have values of 0 here. And there's no way to know for sure if any of these are the vertex, which means I just have 3 points. So this is the scenario in which I'm going to have to use standard form. I'm going to have to write and solve a system of 3 equations in 3 variables. All right, let's do this. So I have more than just 3 points, so that means I have some choice here. I'm going to pick the ones that I think will be the easiest. So that would be 10, 26,900, 20, 30,600, and 30, 32,100. Okay, so remember these are all x, y pairs. So if I take those values and plug them into my equation here in standard form, I would get, for the first one, 26,900 equals a times 10 squared, which is just 100a, plus 10b plus c. For the second equation, I would get 30,600 equals 400a plus 20b plus c. And for the last equation, I would get 32,100 equals 900a plus 30b plus c. Okay, now that I have my 2 equations, I'm going to solve this system for a, b, and c. Now, the nice thing about this is that all those c values have a coefficient of 1, so that's the variable I'm going to eliminate. So remember that this can be tricky. It can have a lot of steps. So we have to remember to label. How do I get different colors? I forget. Oh well. I'm stuck with the green. Okay, so label your steps because could be a lot of work here. So I'm going to use equation 2, and I'm going to leave it as is. And I'm going to take equation 1 and multiply it by -1. So that makes it negative 26,900 minus 100a minus 10b minus c. Cancel 10b, 300a. I'm feeling lazy. Choose 6,900. 3,700. Okay, that's step 1. Step 2, I take 2 different equations, and I do the same thing. I'm gonna do, oh, I forgot, plus 10. I want to be smart about this, so I'm gonna do equation 3 and 2. But I'm going to leave equation 2 as is. I'm going to take equation 3 and multiply it by negative. And hopefully you're seeing why. So that cancels. That's why it gives me negative 2b, negative 500a. Still feeling lazy. 30. It's going to be negative 1,500. Okay. Now step 3. I'm going to take those 2 equations from step 1 and 2 and combine them. So that's 3,700 equals 300a plus 10b minus 1,500 equals negative 500a minus 10b. Those cancel. Negative 200a equals 15, 16, 17, 18, 19, 22, 122, 2,200. So a equals negative 11. Okay. Now that I have an a value, I could plug that into one of these equations to get my b value. So that's step 4. Negative 1,500 equals negative 500 times negative 11 minus 10b. You know what? I'm just going to make them all positive, because if I divide everything by -1, that's allowed. So 1,500 equals negative 5,500 plus 10b. That would give me 5, 6, 7. So b is 700. All right, we're almost there. Step 4, or 5. Pick one of the original equations and plug a and b in. So I'm going to do equation 1, 26,900 equals 100 times negative 11 plus 10 times 700 plus c. Twenty-six nine hundred plus 1,100 minus 7,000, 21,000 for C. And now that I have my values for A, B, and C, I can write my equation, or my function, that models this data. Now, I could say y equals negative 11x squared plus 700x plus 21,000. But I have a context, I have a scenario, and it's specified h of t. So really what I should write is h of t equals negative 11t squared plus 700t plus 21,000. Okay, now that I have the function, I can evaluate that function to approximate the height at which this weightless environment occurs by replacing t with 20.8. And let's see what happens when I do that. Negative 11 times 20.8 squared plus 700 times 20.8 plus 21,000. And we get 30,800 and, let's say 1. Let's round. So approximately 30,801 feet. And that's our answer to that. Okay. Now for this, if you had a table of values that was linear, you would see that all your y values and x values were increasing by the same amount. So if you had like 2, 4, 6, 8, and so on. Now, that's how you determine if a table represents a linear function. But then the question becomes, how do you determine if a table represents a quadratic function, or a cubic function, or a quartic function, and so on? So here's how. When data have equally spaced inputs, you can analyze patterns in the differences of the outputs. So the differences of the outputs to determine what type of function can be used to model the data. Linear data, so linear functions, have constant first differences, meaning when I subtract consecutive y values, I'm going to get the same number the first time around. And quadratic data have constant second differences, meaning after I subtract consecutive y values the first time around, I'm going to get different y values, but then when I continue and do it for a second time, I'll get the same value then. So there's this pattern that appears. If you have a linear function, so remember that's y equals x to the power of 1, they have constant first differences. If it's a quadratic function, x to the power of 2, they have constant second differences. If it would be y to the power of 3, a cubic function, they would have constant third differences. If it was y equals x to the fourth power, do you want to guess what that would be? Yes, constant fourth differences, which again just means that you subtract consecutive y values. So for example, here we are doing 4 minus 9 to get the negative 5, and 1 minus 4 to get the negative 3. So when you're doing that, the first time around, you don't get the same value, so it's not linear. The second time around, you do get the same value, so it's quadratic. If you didn't and you had to do it a third time, it would be cubic. If you had to do it 20 times, it would be a degree 10 polynomial. And so that's what that is referring to. So if you don't know what type of function it is, like in this case, if you didn't know what type of function it was, you can't really do anything with it. The reason why we didn't have to go and subtract consecutive y values in this example, in example 3, is because the first sentence itself says that it's flying a plane in a parabolic path. So that's how you know it has to be modeled by a quadratic function. But if it didn't have that word, we would have had to do the consecutive differences for these y values to confirm whether or not this data would best be modeled with a quadratic function. Okay, next, last example. In reality, in real life data, you don't always see a perfect quadratic function. Sometimes it'll just be best modeled with a quadratic function. So, real life data that show a quadratic relationship usually do not have constant second differences because the data are not exactly quadratic, but they're close. Relationships that are approximately quadratic have second differences that are relatively close in value. So what we're going to look for is the quadratic regression. Now, unfortunately, I don't have the TI Inspire calculator on this device, so I'm just going to talk you through the process. So this table shows fuel efficiencies of a vehicle at different speeds. Write a function that models the data. Models, meaning it's not going to be exact, okay? And use the model to approximate the best gas mileage. So let's just review. To use our calculator to do this, we have to click Control and Dock, and then we click Lists and Spreadsheets. At that point, you're going to get the table, kind of looks like an Excel sheet, and you're going to put X next to A and Y next to B. You're going to run out of space. Then you add all the values from the table. Hopefully you're just ignoring me at this point and doing it from your memory. Okay, then from there, you're going to do Control Dock again. But this time, you're going to click Data and Statistics. At which point, you're going to see a bunch of random points and what looks like a coordinate plane. So at this point, what you want to do is label your X and Y axis and the points you should see move to create a scatter plot. And then from there, you are going to hit Menu, Analyze, Regression. And if you notice, the scatter plot doesn't look anything like a linear function. It actually looks very close to a quadratic function. So when you look at the list of options under regression, we don't want to do show linear. We want to do show quadratic. And then if you remember, an equation is going to pop up on your screen. And from there, you want to use that equation to find the best gas mileage. So again, anytime we're talking about extremes, best, smallest, fastest, skinniest, whatever, it is asking you to identify the vertex. So unfortunately, this is where I leave you, and you continue with your calculator to find, or you should at this point already have, the function that models this data, but what you're going to do now is find the vertex. And that's it.